Hi, ladies and gentlemen. We're going to start the second part of the lesson now about curved mirrors. And the two types of curved mirrors that we're going to be talking about are concave mirrors and convex mirrors. Okay, but what really makes a mirror concave? What makes a mirror convex? If you take a look at the picture in your packet, the fact is a convex mirror always has a curved surface outward. It bulges outward, but because it bulges outward and the way that the normal lines are set up, it's also called a diverging mirror, meaning that as the light rays strike the mirror, they diverge in different directions when they reflect. A concave mirror, on the other hand, a concave mirror, well, the easiest way to remember what a concave mirror is if you use a kind of silly mnemonic. But you think about digging a cave. So if you're digging a cave into the mirror, well, that's what a concave mirror is. It's dug in. But the way that the normal lines are set up with a concave mirror, it's also called a converging mirror. Because it causes the light rays to actually converge together after they reflect, assuming that they all start off parallel. So when parallel lines come in, they all reflect and they all converge through a single point. Okay. Now, when they actually converge and they come in together to that single point, that has a specific name. And that's the focal point, where all the light rays come together and converge. So you can see with this concave mirror over here that when they strike, they all pass through this one point in the center, which is labeled F. But more interesting is that if you actually drew out the entire shape of the curved mirror itself, assuming it became a shape itself, you can see it would form a circle. And of course, at the center of the circle, we have the letter C, and the focal point is always going to be half of the radius. So in this case, we have a focal point where the light rays come together and they will actually generate an extreme amount of heat, as demonstrated in this next YouTube clip. So just watch and listen.
Well, we've got a satellite dish lined with mirrors, and all the sun is coming in, reflecting to one focal point, and then it's really hot. We estimate about 700 degrees. So later on in the day, right now it's about 9 o'clock. Later on in the day, it should get extremely hot. We're going to cook hot dogs out here for lunch.
So why are you doing this?
For mathematics class. The shape of the dish is a parabola, and only parabolas have that property that they reflect to the focal point. It makes one hot, really hot point, which is resembled up by our square unit up there. And when it's later on in the day, we'll have it going, the hottest point going right through that square.
Now, the idea of using a concave mirror to actually heat things up, this isn't new. It's actually as old as the ancient Greeks themselves. In fact, Archimedes was first said to have invented the very first death ray when he took mirrors, well, really polished brass probably, and used them to help focus light to burn the incoming Roman ships that were invading his home country. Of course, we don't know if that's really true or not, and even Mythbusters has done an episode to determine the validity of that statement. But as you guys can see right here, a concave mirror can get really, really hot. In fact,
way the sunlight would all reflect to, and then we built this focal unit out of metal conduit to be able to rest the hot dogs on so we can cook them. So all the sunlight's coming in to focus on these hot dogs to burn or cook anything you want. Put the nose on it.
Okay, so the focal point, where all the parallel rays of light will come together. Okay. Now, if we take a look at the convex lens, though, it gets a little bit trickier. You see, with a convex mirror, sorry, I didn't mean lens, a convex mirror or a diverging mirror, well, the way it's based, all the rays are going to diverge away from each other. They never actually come together, except if you look at them, if you were to trace it out, and you drew the lines backwards, the virtual lines that we had drawn before, like with the plane mirrors, there's a focal point behind the mirror. Now, is that really there? No. But for our purposes, that is where the rays would converge, so we call this a virtual focal point. Okay? While the concave mirror has a real focal point, because that's where the light rays actually go. Now, what are some actual uses for concave mirrors and convex mirrors besides creating a death ray? Well, the most common place you'll actually see a concave mirror, especially girls, is if you go to the makeup counter at Macy's. Because if you've ever noticed, when you go to the makeup counter and you look in the mirror, it shows you a magnified image of yourself, just like in the picture. A diverging mirror or a convex mirror, the most common place is in the store, or actually in gym lockers, where they are security mirrors and they let you see from a wider point of view. And we'll talk about why it does that later. But before we start anything else, we have to talk about how do we actually determine where the image is. And to determine where the image is, you have to learn a little bit of what we call ray tracing. In other words, tracing the rays of light. But before we actually start tracing out the rays of light, there are a couple of things to keep in mind. And I'm going to write these rules down, and you should understand them. Okay? First of all, we're always going to assume that we're going to use the tip of the object itself, which is going to be labeled O, as you guys can see over there. Okay? So all rays will start from the tip. And we know, in reality, when light strikes the tip of the object, it bounces off in every which direction. But the one that's going to be the most important to us is the one that's going to be bouncing horizontally, or really parallel to the axis itself. Okay? Because when it bounces horizontally, and if I were to trace it out, when it strikes the mirror, based on how the normal line is drawn, it's going to always reflect through the focal point. Okay? So the lines that you're drawing, the very first line that you draw is parallel to the axis, and then it reflects through the focal point. Okay? The second line you're going to draw is actually the exact opposite of that. Because if you actually have one of the rays of light that are going in random directions, if it actually manages to go through the focal point, well, based on the way the normal line is, because it's just going backwards, it's then going to go parallel to the axis. So the second line you're going to draw is through the focal point, and then it reflects back parallel. Now, there are actually many other lines they can draw, because technically they should all meet at the same point. And where all those lines meet, that's where you have the image created. So if you take a look at this final image over here, okay, you can see that when you have the first line go parallel then through F, notice where the person's eye is over here. He's looking at the object, which is held in front of him, in front of the mirror. Okay, so if there's a mirror over here and he's looking at a pen in front of the mirror, this is how he would see it. The second line goes through F, then reflects back parallel. And where the lines actually meet, that's where the image is perceived. So if he were looking at the mirror, he would actually see the object to be upside down. Now, if you notice some other lines, and these are possible ones that you can do as well, the third possible line is just straight through the center. So it's just basically, if it strikes through, it strikes exactly on the normal line at this end. And since it strikes on the normal line, it just bounces right back through C. And one that they don't show you on this picture is if you draw to the center of the mirror itself. Meaning if it hits the center of the mirror, it hits when it's perfectly vertical, and then it's going to have the exact same angle coming off, and it's actually going to go through as well. So all of these are possible lines to be drawn, but we're going to practice this some more. Okay. Now, if you take a look at this diagram over here, okay, we see the candle as our object, and we see our object and we see our image. In this case, we can see the image is actually directly under the object. And the two lines that they use in this case over here is the one that goes parallel and then through F. And the second line they say is if it strikes straight at the center of the lens, it reflects back at the exact same angle. And over here, you can see that overall, that's where the image is going to be created, where the lines are going to converge. We'll come back to this, but I want to show you, actually, what happens to the image depending on where you move the object around. So take a look. When the object is very far back, we can see that the image is smaller than the object itself. And when we're in class later, I'll give you guys some mirrors and we'll actually look at this. But the closer and closer you move the object to the mirror, the larger and larger it appears. In fact, but still upside down. But when you move past the focal point, and this is, girls, when you're looking at that makeup mirror, when you're holding it up close to your face, and you see that enlarged image of your face. Well, that's what you're really seeing. In this case, we're seeing a virtual image. Now, why is it virtual? Because the rays of light aren't actually going through the mirror, and the image is being created behind the mirror itself. Okay? Keep in mind, of course, when I said that this was virtual, notice it's also right side up. Because virtual images are always right side up. But before, when I was creating a real image, by moving the candle further back, over here, you can see the actual yellow lines create that image. And when that real image is there, notice it's inverted. Because real images, for us, are always going to be inverted. So please make sure you note that. So this is the example of when you hold the mirror up close to the object itself. So when the candle is actually very up close to the mirror, you can see that it's larger than before. But this is, of course, a virtual image. While if you hold it further away, sorry, I forgot an example to show you guys. besides the makeup mirror, dentists also use this. And you can see over here that with the dentist, or not. Okay, we'll come back to that later then.
Let's see what happens after we turn on the cycling.
Okay.
Recharging or exchanging batteries.
So in this example over here, you can see that with the concave mirror, it's creating, because it's held so close up to the teeth are inside the focal point, and it creates a virtual image. So whenever a doctor looks inside your mouth, he's getting an enlarged image of your teeth from behind. But of course, if you hold it further away, that's not what you see. When the object is further past the focal point. So if you guys note, here's the focal point, and the object is all the way back here. Okay? When the object is held behind the focal point, it creates a real inverted image. Okay? And that's just the way that the lines are going to draw out, and that's what we actually see. So, here's your first example on your page, and let's label a few things together. First of all, hopefully you guys note this is the focal point, and the focal point is exactly going to be half the center. Over here, I want you to note, here's the object, so I'll label that as O, and the eye is going to be back here. That's looking at the object inside the mirror. So what does the person see? Well, we follow our lines parallel and then through F. And then through F, then parallel. We can see that the lines actually are going to converge back here somewhere. Now, 2 lines is the minimum they should do, but generally you should try to do a third line as well, using a ruler, of course, as a check. So you can use your third line as through C as your check. And it's slightly off, but it's close enough without a ruler that I can see that this is the approximate location of the image. Now notice the red dot is below the axis. So because it's below the axis, that means that the image is upside down. So here's the image. And of course, because the image is upside down and is created by the rays themselves, this is a real inverted. And in this case, hopefully you guys can see that it's slightly larger than the original arrow and larger image. If we look at the next example, okay, this is the example of up close with a makeup mirror. And this one gets a little bit trickier. The first line you want to draw, of course, is still parallel and through F. Let me label it F and C. Okay. Now, the second line is supposed to be through F and then parallel. Okay. Now, when I go through F, F is behind the object. So even though F is behind the object, okay, I know I'm not going to hit the mirror. It's not going to reflect going that way. So I extend it to where I think the mirror would be normally. And when I extend it past, it's going to reflect back parallel. But these lines aren't going to meet. We can see that they're spreading apart from each other. So even though they're spreading apart from each other, on the real side, they can meet on the virtual side. And whenever I draw virtual lines, I basically extend backwards the reflected ray. So in this case, the top line was reflected, so I pull that back. And with the green line, okay, the diagonal line was reflected, so I'm going to pull that one back. And where the two lines converge, I get my image. As a check, there's several you could do. You could go through C, you could draw it to the center of the lens. In this case, I'll draw it to the center of the lens. I'll draw it right here as my check. It goes there, and normally it bounces back at the exact same angle, which again won't meet on the real side, but I know that if I pull back that reflected ray, it will meet on the virtual side. So this is a virtual, larger, and upright image. Okay, and that's what you guys should be drawing right now as well. Now, this last example is actually slightly trickier. In this example, the object is on the focal point. And what happens if the object is on the focal point? Well, let's draw lines and see. So in this case, I go parallel, and then I go through F. And normally my second line is through F and parallel, but that's a little bit tricky, right? It's not really going to work because I'm on F. So rather than, I'll just skip that line. I'll draw the third line. I'll draw a check line. And the check line could be either through the center, C, or it could be drawing to the center of the mirror itself. Okay? Either one's fine. In this case, I draw to the center, and then it's going to reflect back at the exact same angle. But note, what's happening when it actually reflects? Are these two lines ever going to meet? In this case, they are parallel to each other, so the answer is no, they're not. Okay? And if they don't meet, that means that the answer is actually no image is actually created. An example of what uses this is your regular flashlight. If you think about how a flashlight or even a car headlight is shaped, you've noticed hopefully every flashlight has like a little cone around it, right? And inside the flashlight, you have your bulb, and basically you have the battery inside over here. Okay. A little bit too detailed. But the fact is, the way this bulb is set up, the bulb is that over here, all we have is a concave mirror. And the bulb is actually placed at the focal point of that concave mirror. So, I mean, all the light that goes out gets generated out without ever creating an image of the bulb. Because no image will be created when the object is placed on the focal point. And again, car headlights work this exact same way. So, no image. Okay. Our final example over here for the concave mirror is about when the object is placed on the center instead. Again, I'll label it. And note what happens. Over here, as I go parallel, then through F, okay? Second line, of course, would be through F and parallel. Not the best line, I apologize, but close enough. My third line will be a check, either through C or straight through the center of the lens. Either way, I'll just cheat and just say through C itself. And over here, I actually get my image. And notice that the image is exactly underneath. And because it's exactly underneath, it's real, it's inverted, and it's the same size. So that means, and because it's the same size, it's actually placed at the exact same location as the object itself, which we're going to write down in our notes in a moment about the relationships between size and distance, but I just want you guys to know that it is the same size. And let me show you guys an example of what happens when it's there. Because, as I told you before, okay, these are real images. That means the image is actually there at that location. You might see it in the mirror, of course, but here's an example of a magician's illusion. There's a marble, or stone, on top of a bowl. A stone, actually. And when he tries to pick it up, he can't. In fact, his finger is passing right through the stone itself. But you guys see the stone's right there. But in reality, it's not. The stone is placed at the center of the top concave mirror. And when it's placed at the top of the concave mirror, it actually generates that image.